welcome everybody to this webinar today. My name is Dana Parrish. I am the Senior Customer Success Manager for Dassault Systems SOLIDWORKS, joined by Ramesh Lakshmapathi, who's our Senior Industry Process Consultant. And we're both on the, again, the simulation team. You saw that video, and it's a really great video, just kind of giving a high-level outline, a real customer success story of success designing and simulating industrial equipment and using our next generation simulation tools. So we're going to go a little bit deeper into that. Let's talk a little bit about industrial equipment and segmentation. You saw a little bit of it on the video for you folks that got in a bit early. Industrial equipment covers a lot of stuff from the heavy equipment that we see for construction and for agriculture and things related to that. We have automated equipment, machinery, bearings, any type of process equipment, stuff like that. I mean, it's just a very large and vast type of segment, industry segment. Within our world at SOLIDWORKS, that is one of our largest, if not the largest, industry segment that we have many customers in. So we look at some industry challenges here. And first one is, look, you want to make, if you're designing any type of equipment, machinery, what have you, you want the parts of that of the equipment, as well as any of the overall machine itself to be very durable. That means it's going to last a while. It's not going to break down every year or something like that. You want to minimize operation and usage costs for your customers. That's a key, and that can be a key competitive advantage. We have a lot of emerging markets around the world that are opening up. You know, in addition to China, as we hear about all the time, you have India, Brazil. You even have things being reshored back to the United States. So there's a lot of opportunity in emerging markets, and because of that opportunity, now there's competition. So you want to be able to at least have some differentiators against your competition, and simulation can definitely be one of them. In addition to that, we have mass production and mass customization. On the mass production side, you've got all the heavy equipment that's used all around the world to do different things. Then on the customization side, you have different types of machine tools that do different things, different types of process equipment that do different things unique to an industry or unique to your business. So we have a little bit of both. You have mass production and mass customization, and we have to be able to cover that. And there's some really interesting trends as well. Right, the machines that are being created for process, for machinery, things like that, automated type stuff, they have to adapt to different use cases. And being able to use maybe one machine for different use cases is key. But these machines have to be smarter and flexible. We'll talk a little bit about that at the end with some of the additional tools. But being a smart machine, being able to talk to others, talk to you, and being able to be more flexible and being able to do more and neat and innovative different things to try to beat your competition. And look, if you look down here in this slide here, those are all different Vermeer products, right? So you have a large product portfolio, and you want to have a large portfolio so you can remain competitive and cover different, I'll call it sub-industries of the industrial machine and industrial equipment vertical market. So it all starts with simulation as part of the successful design, and there's different building blocks that we have here. We have structures and within our world that's the abacus solver for structures. You're going to see that in a little bit. We have a multi-body type of simulation, durability, which is the fatigue, acoustics, electromagnetics, fluids, automation, and optimization. Know that within the Dassault Systems SOLIDWORKS, that there are several tools available that can cover all these different types of simulation building blocks. So here's a quick agenda. I'm going to introduce Ramesh in just a second here. We're going to start by finding the best design. We're going to look at some structural integrity. Then we'll look at some advanced structural analysis. And then that'll be Ramesh. And then I will come back and talk about some of the other physics that are out there. And then we'll wrap it up with Q&A and some next steps or call to action. And so without further ado, I'm going to turn it over to Ramesh, and let's go find the best design in some of our machine parts there. Ramesh?
So what we're going to do is, you saw in the introduction video, the resume was actually one of the customers highlighted. And so we're going to take their assembly. So the resume is a SolidWorks customer that it's a top international manufacturer based out of Lima, Peru. And they make underground drilling machinery and related equipment that provides a better and a more cost-effective alternative to use of traditional drilling rigs. So for this first section, I'll be actually using a sub-assembly part from the leading mining equipment, which is called the Bolter 77D model. Okay, and the question is, am I going to analyze the full assembly as shown here? And probably not, right? With simulation tools, the best way to work and achieve a success is a crawl, walk, and run approach, right? So we want to focus on the most important and the critical pieces of the assembly rather than taking the entire assembly in the first go and then running into issues. So let's drill this down a little bit more to focus on this bracket assembly, which takes on the brunt of the loading. You can see how the entire boom assembly can technically, it's cantilevered to this bracket, and this bracket actually has a knuckle joint. And we'll analyze this knuckle joint as a designer. So as a designer, let's say I'm in charge of the design process, but I'm also in charge of basic simulations. And that could be just understanding the strength of the part, right? Or being able to do a couple of design iterations, taking the design of this knuckle joint from point A to point B and come up with an optimal design. Then as a designer, I can actually pass on the best design to, let's say, the engineer or the analyst within the company. And that person could actually do a more comprehensive, a more complete simulation of the entire bracket assembly. So let's get started with looking at designer level simulation. What is this entitled, right? So as always, I'm going to start off in SolidWorks. So I have this bracket assembly, and it's only just half bracket assembly I'm going to analyze. And that's a nice thing about simulation is you can take advantage of symmetry in the model and really simplify the analysis time, simplify the simulation itself. So the first step is really before I start using simulation, is to push this geometry through this connector that you're seeing here into the 3D Experience platform. That's where my simulation tools reside. So it's a simple save operation, and that's exactly, I'm going to push all the elements of this assembly, all the parts of this assembly into the 3D Experience platform. So it's just a work folder on the cloud where all the files can be saved and converted into a format that can be used not just for the simulation tools, but also by other applications that can be relevant for your analysis needs. So all I'm doing here is waiting for a green check mark. So that way I know that all the files have been uploaded. Once I get a green check mark, then within SolidWorks, I can actually go ahead and launch my linear structure validation. So this is the simulation tool that allows me to do linear static analysis and any linear analysis, like maybe buckling or thermal or maybe even frequency analysis. So I'm just launching it right from within my SolidWorks desktop. And once the model is actually loaded up into the platform, I can start my simulation process. All right, so let's go ahead and, okay, there you go. So all I have to do is get started with my simulation. The first step is really what's the type of analysis. And as a beginner, let's say as a designer, rather, I want the program to guide me through the process. So I'm going to use the system that you're seeing here on the left side of your screen. So I'm going to go ahead and say, okay, I want to set up my simulation. Let's give it a unique, define a unique name. Let's call it as boom bracket simulation. Very simple step. That's basically done. Next, I'm just going to go ahead and apply some mesh options. I'm going to turn on the adaptive meshing. So as a designer, I don't want to wrestle with the meshing, but let the program automatically hone in the best meshing for me. So that's what adaptive meshing does. And all I'm going to do is just go ahead and tell the program to mesh. Then I'm just going to go ahead and tell the program, look, I'm as a designer, I just care about the knuckle joint. So I'm just going to exclude all the other parts of my assembly. A very simple unchecking of the options helps me get to the the geometry that I want to analyze. Okay, so the green part is the geometry I want to analyze. The gray ones are the ones I exclude from the analysis. Next, I'm just going to go ahead and apply some materials. So the nice thing about the 3Experience platform simulation is it comes built in with the material palette. So there's a library of materials ready to use, or also, or if you want to define custom materials, that's also an option that you can that you have access to. So here I'm just going to search for ASTM, just filter down my laundry list of materials. And there you go. So I have my simulation. I can verify some of the properties of this material and simply hit apply. And what I'm going to do is just grab one of the parts from the screen and propagate the selection to all the parts that I'm seeing on the screen. So in one single click, I can apply the material to all the parts of my assembly. Now there's contact, but really in this analysis, I don't want to simulate any physical interaction, but rather more of a bonded condition. So there's a tool that you're seeing here that allows me to simply quickly find out all the contact, all the touching faces, and simply apply a bonded condition. So you can see that's super easy, super fast. That's basically done. I don't have any connections in this assembly, but we'll see that later on. But right now, I'm just concerned about simulating the physics. So I'm just going to grab these gaskets, metal gaskets on the top and bottom, and I don't want these gaskets to move in the vertical direction. So that's the boundary condition I'm applying here. Then another thing is I'm going to grab these conical faces and simply constrain the radial motion or the radial deformation of these conical faces. The last thing I need to do is apply a load. So here is a bearing load. I'm going to select those two faces of interest, and I'm going to orient my coordinate system on the fly. So I'm just going to tilt it by about 45 degrees so I can get the X direction of interest and apply a 20,000 pound force as the bearing load. So very simple steps. So basically this assistant is a great way to get started and guide us through the setup process. So last thing I need to do is simply give this guy a spin. So I'm going to simulate the analysis. And the couple of things you can do. So you can run the simulation on the local machine, or if you don't have the hardware infrastructure, we can also run the analysis on the cloud. So here I can run, this is a simple problem. I'm going to run this problem on my local machine, take advantage of all the 4 processors that I have, and run the analysis. And so right now it's actually cranking through the analysis. I'll take a few seconds to come back with the results, and we'll just investigate some of the key results, such as factor of safety, maybe the displacements, how the structure is actually deforming, maybe even look at some of the areas where there are tensile and compressive stresses. So we'll see in just a few seconds what are some of the key results you have access to once the analysis is done. So here I'm looking at the default 1 meter stress plot. I can do a lot of things here, but really I want to get started with looking at the animation, right? How the structure is deforming, is it bending, twisting, shearing? If so, in what direction is that acceptable? But right from the graphics area, I can switch to a displacement result, or maybe look at the factor of safety. That's about a 1.3 minimum factor of safety. And then, I can look at a bunch of other results like displacement vector. I can get more granular information as to what the direction of deformation is, or, how the reaction force are actually getting reacted at the support locations. So I can get a very high, rich visual of the different types of results. And here, for example, I'm also looking at where the tensile areas are, where the compressive areas are. And so there's a whole bunch of results that get created right off the bat. And as a designer, I can skim through all of these results to make some design decisions. So I have factor safety 1.3. That looks pretty good, but maybe that gives me an idea. Maybe in terms of I can reduce the thickness of these extrudes and maybe change the radius, maybe make this entire knuckle joint a little bit lighter. So I'm going to go back into SOLIDWORKS, and the first thing I want to do is just reserve this. So reserve is nothing but it actually allows me to have access to these files. So that way, if somebody else is working on this assembly, I don't accidentally override it, right? So all I want to do is just go ahead and make some changes to the dimensions on the knuckle joint. So I'm just going to grab that top face and also the radius. So I'm going to change the radius value. Let's say it's 30 millimeters. So I'm going to just specify about 10 millimeters radius. Okay, and then likewise, I'm going to grab the other dimension that controls the thickness, and I'm just going to make it, so right now it's 30 millimeters. I'm going to change that to about 20 millimeters. A simple step, basically done. So you can see how I've reduced just lightweight of the design. And once I do that, all I have to do is push this new design through this connection back into the 3D Experience platform to continue with my simulations. Okay, so again, we are designing and simulating side by side, right? Even though we're using SOLIDWORKS Desktop for our design purposes and we're using the simulation on the 3D Experience platform, they are actually connected through this interface. And that way we can drive design changes very quickly, and it's completely associative in nature. So that allows us to try out all these multiple design iterations as we are designing and simulating side by side. So that looks pretty good. I've actually, so I'm going to come back into the 3D Experience platform simulation. And what I want to do is just refresh the environment. So that way it'll detect, if any changes took place on SOLIDWORKS side. And you can see that right off the bat, I have, the design propagate to my simulation environment. And at this point, I'm not doing anything other than re-simulating this new design. The mesh automatically updates. All I have, the physics remains the same. So I'm just going to go ahead and rerun the simulation. A very simple step. So this way, I can try multiple flavors of my designs very quickly and see what that design's performance looks like. So let's see. Let's wait for the analysis results to come back. And I'm most interested in looking at, again, the factor of safety. All right. So again, a great way to be able to take something as simple as this knuckle joint at the designer level, and then be able to do multiple iterations of the design and make the design a lot more better. And you can see the factor of safety most after right now it's about a 1.07. So that's still acceptable. But at this point, I want to hand off this design to my analyst or to my engineer in the company, right? So I'm going to take advantage of some web tools on the 3D Experience platform, but I'm just number one, what you're seeing here is I'm going to make a copy of the simulation, and make that copy available to my analyst. So what this allows me to accomplish is also the fact that though I make a copy, the design for both my simulation at the designer level, as well as the simulation that the analyst is going to work on, that both these simulations are going to be tied to the same exact SOLIDWORKS design. So in the future, if the design changes, then that design change is going to propagate to the designer level as well as to the analyst. So it's a nice way to actually exchange information in one single environment and with a connected set of tools. So the process that you're seeing here is the process using a web browser. So I'm just giving it a new name, but I'm making an exact duplicate copy of my simulation, my finite element mesh, and my geometry in one single go. And once this operation is completed, I can let my analyst or my engineer know that he or she can access the duplicate copy for doing a more advanced or more comprehensive simulation. All right. So what happened is so the duplicate copy is what the analyst or the engineer is opening using a more advanced tool, simulation tool on the 3D Experience platform. And once that is done, then we can actually move on to the next step where the analyst is going to do a more complete simulation. So what I want to do is I'm just going to switch back into the 3D Experience platform real quick. So I'm not going to be showing you just PowerPoints today. So this is my 3D Experience platform. So as the analyst, let's say, for example, I did this full analysis. So I see the knuckle joint that is being used as part of the bracket assembly. So as an analyst, let's say I have done the simulation, but what I want to really highlight here is not walk you through, start to finish the entire process, because you've already seen that, at the designer level, right? How the simulation is set up and run. The same concept, same workflow exists for the analyst or the engineer. But what I want to focus on is a few key areas, technologies on the 3D Experience platform. So, for example, I run the analysis on half the geometry, right? So what I want to do is quickly mimic this. I want to be able to take a symmetry, mirror the results about the symmetry plane. So when I'm documenting the analysis results, my boss is not saying, hey, what happened to the rest of the model? So I have, even though for simulation, I made it super simple, analyzing half the geometry, for the full simulation, for the I can visualize the full results, as you can see here. And you can see as I'm moving the mouse over the geometry, I'm actually getting some values. So those values are nothing but the current result, which is the displacement result. So the displacement is actually being shown at the location of interest. As I hover the mouse, you can see those values. Okay. So there's a lot you can do here. So let's go ahead and animate this. And you can see that just analyzing the knuckle joint versus the full assembly, this is a much more comprehensive, more complete simulation that allows me to get a much bigger picture, more granular picture, I would say, in terms of analyzing this entire bracket assembly. So I can see how these knuckle joints are actually moving. I have the bolt connections. I'm using some bolt connections to tie up the knuckle joint to the bracket part, and so one of the things I might be interested in analyzing is, what are the bolt forces, right? So here, for example, I can quickly go to my XY plot result, and I can just quickly go ahead and activate the XY plot. Let's say, so I shouldn't have not the definition. I just want to view it. So there you go. So this is interesting in the sense, this is actually a force versus time, but it's actually telling us what the bolt loading looks like in the system doing the deformation. So initially we're applying a preload in the bolt. So that's a linear part of this this plot. And then as soon as I apply the bearing loads, so the bolt loads actually exhibit a nonlinear behavior. So that's pretty interesting to note. But it gives us a good idea of what is really happening in the bolt. Even though we are not modeling the bolt, the physical geometry, or including it in the actual analysis, I can still use these virtual bolt connectors and get some of the key results that will help me make some good design decisions. Is this bolt good enough? Can I get away with the existing bolt I'm using, or do I need a bigger size bolt, or can I get away with a smaller size bolt? So those are the type of that type of information can be really crucial from an engineering perspective when we are using fasteners to connect two or more parts in our assembly. So this is just the results side of it. I want to actually go ahead and now highlight a few things that's really nice to understand. So the first thing I want you to notice is this: we're using a coupling. So a coupling is a way to actually transmit a load, a remote load in space. So here, for example, we are not modeling the boom that's connected to the knuckle joint, but rather we are using a coupling connection to transmit the actual load onto these two cylindrical faces on the knuckle joint. We are also using screws, so standard screws. So that's the virtual connector I was talking about. So you can see that there is no, the geometry, we're not modeling the geometry, but we are just using a virtual connector. And there's a whole bunch of connectors, as you can see here in the bottom of the screen. We can use a virtual bolt connector, or a pin connector, or a tie connector, or maybe line fasteners for simulating weld connections. So there's a whole laundry list of different types of connections, virtual connections, that can be used on the 3D Experience platform to simulate the connection between two or more parts of your assembly. So the other one is the meshing. So you can see the mesh is displayed on the screen. So let me just clean this up a little bit. I'm just going to go ahead and hide the geometry, so that way you can see the mesh. So I'm going to zoom in. You can see that this gasket here, I'm actually modeling it with using hexahedral elements, hexahedrons, and the rest of the assembly is using tetrahedrons. So I can mix and match different element types. So as an engineer, as an analyst, I would like to actually be able to have full control over meshing options, and that's exactly what you see here. And down here, down at the bottom in this menu, you can see that we can do a beam mesh, a triangular mesh, a quad mesh, tetrahedron mesh, and also a variety of hexahedrons such as a sweep mesh, partition hex mesh, hex dominant. So there's a lot, and there are some advanced meshing tools also available for you as an engineer or an analyst to be able to take a deep dive into controlling the mesh. All right. The next one I want to point out is, let's see if I can, yeah, so let me just go ahead and look at some of the materials. I want to bring up the material, even though in this case we use a linear material, but what I want you to see is the options, the material options that you have on the 3D Experience platform. So there's a lot of different types of material behaviors that you can use and combine together in a single analysis. So you can see that there's elastic effect, you can also do plastic effects, and there's a lot of different types of advanced material models, like not just plasticity, but if you are trying to simulate like maybe a hyperelastic material, maybe a foam material or a gasket material, or you want to combine that with some other physical effects, such as maybe a thermal stress or thermal properties that could be useful for you if you want to do a thermal stress analysis. You can combine your structural properties with other thermal properties or other fluid properties as well. So there's a lot of different types of material models available for you to simulate the exact and the real behavior of your material, right? So that's one thing. And the last couple of things I would like to highlight is let's go here to our scenario, which is our physics environment. And here I want to actually highlight one key technology that's called generalized contact. So generalized contact is a unique abacus technology. And switching on this option literally means that we are not turning on any, we're not defining any contact conditions, okay? So that way, it helps to eliminate the upfront guesswork we otherwise have to do to define those contact definitions, right? So here, during the solve, the program will automatically determine all the contacts that might happen between multiple geometric entities, right? But what we can do is we can actually control the contact behavior. So for example, I can tell the program, I want to include, let's say, a coefficient of friction in my contact definitions, or I can control some of the tangential, the normal behavior of the contacts. I can also turn on contact stabilization, which is really a powerful tool. So a lot of times when you have contact analysis, you might run into stability issues. So by turning on contact stabilization, the program actually allows for the solver to actually be able to go past an issue with the contact. Maybe there is chattering in the contact area. Maybe there is some unbalanced forces in the contact area. So the contact stabilization will actually take care of all of those things and make sure that our problem runs to completion. And the last thing that you saw, obviously, in the earlier setup was being able to run the problem on the cloud. Okay, so if I do a simulate, hopefully this will bring it up in just a few seconds. So obviously what I want to show you is, for example, oops, sorry. This, yeah, so there you go. So basically you can run the problem on the cloud, or you can run the problem locally as well, right? So what happens is, on the cloud, if you choose to run on the cloud, you have access to running the problem up to 144 cores with more than 100 GB plus memory. So think about, if you don't have the infrastructure or the hardware infrastructure within your company to run these large problems, or if you just simply want to run the problems much faster than what you're used to, so you want to take advantage of the cloud compute option that is also available on the 3D Experience platform. All right, so just to recap real quick, we saw the initial design at the designer level, right? We're looking at the knuckle joint design, and we looked at a factor safety of 1.3, 1.4 initially, and we also were monitoring the mass. Then we said, okay, let's make a quick design change and look at the final factor of safety, which is a 1.1. And obviously we were successful in reducing or lightweighting the knuckle joint design. But then, you saw how the designer actually passed on that analysis as a duplicate to the analyst, who took that duplicate simulation made all the changes necessary, made a more comprehensive setup of the simulation to get an idea of what the entire assembly response looks like, what the bolt connections forces look like, and so on, right? So basically, it's a complete loop in terms of a designer doing design, doing some basic level simulation, and then and then the analyst coming in and doing a more complete and comprehensive simulation. We also saw, like, for example, going from simple to detailed simulations using a virtual bolt connector, how we can actually request or get some key results of interest, such as bolt forces. And you can use the same workflows, the same process that I showed you to scale your simulations to a much more complete analysis, such as this full boom assembly analysis, to answer some simple questions like, hey, can the boom sustain the maximum working load of 40,000 pounds? Are the plate reinforcements enough to prevent a local buckling effect? So you can analyze all of those additional physics. Moving on to the next segment, which is understanding some of the other structural integrity issues that might be relevant in the industrial equipment industry. Let's start with the global stability evaluation of this excavator, right? Some of the key questions that you might want answers to using simulation is it structurally stable? What happens if the arm is expanded to the maximum length and the bucket is loaded to its full potential? What if the upper body rotates by 360 degrees? And what if the counterweights are in unfavorable position? So a lot of these things you can get answers to using simulation. So for example, you can see this entire assembly is being analyzed on the 3D Experience platform, and all we care for is looking at if the maximum dynamic stresses on the structure is acceptable or not. We can also go ahead and look at other elements, right? For example, if you look at the excavator itself, there are so many parts that undergo repetitive loading and unloading operations, and perhaps understanding the structural integrity of the plates connecting the main boom, let's say, and the bucket could be important in terms of how durable it is, right? Because if the plate breaks, that means it's failure of the entire system, and it's also a safety issue. So what we can do is we can actually end up doing a fatigue analysis, but on just the plate part alone, and compare an initial design and a second design that's more it's modified, but it's a best design that helps to increase the fatigue life. So fatigue analysis is a great extension to doing static analysis in order to be able to paint a complete picture of your designs. So let's look at some advanced structural analysis that might be of interest. A lot of times, you have to satisfy international standards such as the ISO 3164 or ISO 10262, and there could be lab evaluations of protective structures, or what we call as ROPS, or rollover protective structures. So this example over here is actually illustrating what Resumin as a customer does. So on the left side, you're seeing the video of the actual crush test on the cabin, on the roof of the cabin, where the operator is actually sitting. And then on the right side, you're seeing the simulation of the exact process. All right. So this is absolutely essential, because when you're actually simulating ROPS, it could be an industry requirement. You have to satisfy protocols as per the industry standards and make sure that the energy absorption of the structure is in accordance or within the threshold limits specified for that particular design. So here what you're looking at is a crush test of the side load and a top load of the same cabin assembly. And at the bottom, you're looking at force was the displacement response, the area of which will actually give you the energy absorbed in the structure. And a lot of times, you can also model on the 3D Experience platform, you can also include damage, what is called as damage modeling. So it's just not plastic effect that you want, permanent deformation effects, but there could be a scenario where you want to see how the structure starts to disintegrate, right? So we call that as damage modeling. So where the structure loses its stiffness completely and in the plastic phase, and then starts to break apart. So you can model that, what we call as progressive damage modeling on the 3D Experience platform. So next couple of examples real quick is, this is APCO, another SOLIDWORKS customer. So you're already seeing is a weldment frame, and right at the top, you can see there's a robotic arm. And this robotic arm actually is a pick and place machine. And because of the motion, it induces vibration on the weldment structure. And what we really care about is this electric cabinet that's sitting, that's marked, shown as, the center mass of that electrical cabinet is what is of interest to us. All right. So because of vibration, we want to make sure that we don't see excessive vibration in the cabinet assembly, because there's a lot of electronic components, electrical components that can actually get damaged because of vibration effects. So a few good questions to analyze here using simulation is, what is the maximum dynamic stresses on the frame? That's easy, but the key thing that we are after, or the key KPI is resonance and issue, is acceleration response on electrical components. Okay, so using the 3D experience platform simulation, we can again take this weldment structure. Again, we're not including any of the details of the cabinet, electrical cabinet, or the motor sitting on the top. But that's the beauty of doing simulations like this, is we can still get a lot of critical information, like how is the weldment structure vibrating, and the plot here on the left side is nothing but the acceleration response at the center of mass of the electrical components. So that's actually a remote point in space, but you can easily actually get the key KPIs of interest and see if the design is structurally safe or not. Another nice example is an overhead rail system. So this rail system, for example, it's like a big bucket, right? Carrying a lot of load, and this could typically you could see this in a factory shop floor, right? But what we are concerned about is, what if this rail system is moving and then suddenly it has to come to a sudden stop? And is that going to create an undesirable response in the system? And is that going to cause the center of mass to shift excessively? So, or what's the overall reaction force or moment at the support location? So very similarly, again, I'm just showing you different examples that could be relevant. But this is showing, for example, if the structure comes to an abrupt stop, what happens to, what's the visually what will happen in terms of vibration effects and how that affects the displacement, overall support reaction loads. And with that, I'm actually going to hand it back to Dana, who's going to cover a couple of other sections in this presentation and wrap it up. Dana?
Perfect. Great job, Ramesh. Thank you so much. So this is what I call, but wait, there's more, right? We talked all about structural, but we do have some other functionalities as well that can certainly help with your design and validation of your components and your assembly. So first one is our fluid dynamics engineer. It's a very, 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 very broad and diverse tool, being able to do all things related to computational fluid dynamics. You can see some of the highlights: compressible, incompressible, Newtonian flows, and the non-Newtonian. We have some additional turbulence models, the K epsilon and the K omega. We have RANS, a RANS-based model now for turbulence, as well as better, more robust meshing, things like that. So it's a full-blown tool running on the 3D Experience platform for computational fluid dynamics. So certainly something to consider as well. A couple of examples here, as you see, things you can look at with our CFD tool: exhausts, wings, drug delivery, electronics cooling, thermal design for engines. All different types of really, really cool stuff that you can do with our 3D Experience Fluid Dynamics Engineer tool. Another one to look at is, this is new to our family. We have now Electromagnetics Engineer, which now we bring into the fold electromagnetics, and this is for both low and high frequency applications. It's based upon the CST Studio Suite tools. And I won't read everything here, but anything related to any type of 5G connection, IoT stuff, right? That's becoming an important component of successful machinery design, is the IoT aspect of it. And so there's different applications here. So it's a full-blown electromagnetics and electromagnetic interference and compatibility type of tool. And again, if you're looking at IoT type applications for your machinery and industrial designs, this is what you have. Okay, so let's kind of wrap this up. As you saw, Ramesh really worked through and found a really good design. You saw a lot of information that you can extract from the 3D experience simulation tools. We talked about instructional integrity to establish a safe working environment. Also throwing in some complex physics. You know, we do offer some complex physics in terms of an explicit solver, which now enables you to do crash testing, impacts, and things like that, drop testing. And then we talked about some of the other physics. So keep in mind we have computational fluid dynamics as well as electromagnetics to complement and enhance the 3D experience mechanical simulation tools. So we'll go ahead and wrap this up. We're about right on time. So what's your call to action here? For sure, I would go on to our website, 3ds.com, and it's kind of a long title here, but go into products and services and you'll see the Simulia link there. And then within there, we drop down into the different types of industries, industrial equipment being one of them. So if you just go to 3ds.com into products, services, and Simulia, you should be able to get to it pretty quick. We also have a Simulia learning community. So you can go there and join up and get updates and refreshes, look at, talk to other people, look at the different types of e-learning that we have out there, and get up to date on any latest releases, anything we've added, enhanced, and stuff like that. Great place to go learn more about the tools that you've seen today. Always call and talk to your local provider. In this case, it's MLC CAD Systems. We have an awesome relationship with these guys. They do a fantastic job. They've got the infrastructure in place to support all of these tools, and please contact them.